As 3I Atlas emerged from perihelion, it was evident that it was no longer the same body that had quietly entered the inner solar system several months prior. Observers had previously seen a subdued glow dominated by dust, but now a remarkable transformation confronted telescopes worldwide. The comet had taken on a vibrant green hue. Enveloped in a radiant emerald halo, the comet's change was unmistakable, signaling a significant metamorphosis happening in real time. For an interstellar visitor already steeped in fascination, this abrupt color shift introduced a new level of intrigue, prompting astronomers to inquire not just about what had changed, but how much of the comet's concealed interior had been brought to light by the relentless heat of the sun. Before perihelion, 3I Atlas appeared rather muted. Its coma exhibited colors consistent with sunlight reflecting off dust particles, generating warmer reddish hues, typical of an environment rich in dust. This phase illustrated a familiar narrative of loose materials being gently released as the comet warmed, without any vigorous gas activity dominating the scene. Then came perihelion, the point of closest approach to the sun, where solar radiation reaches its peak intensity. It is at this juncture that comets are pushed to their limits, their surfaces cracking, and deeper layers coming into contact with outer space. Upon receiving new images post-passage, the change was immediate and indisputable. The coma had decisively shifted toward green, and the narrative was no longer controlled by the dust. High-quality observations from the Gemini North Telescope captured this transition vividly. By utilizing multiple optical filters, astronomers created composite images that distinguished between light reflected by dust and light emitted by gas. The evidence left little doubt. The coma following perihelion was dominated by emission lines rather than sunlight reflection, with those emissions perfectly aligning with the wavelengths associated with diatomic carbon, or C2. This molecule has long been recognized as the source of the bright green glow evident in many active comets, especially when they undergo intense heating by the sun. In the instance of 3I Atlas, the green coma was not merely intriguing, it represented a classic response to solar excitation. The physics underlying this transformation is well understood, yet witnessing it remains incredibly compelling. As volatile ices sublimate, they release parent molecules that are quickly fragmented by ultraviolet radiation. Among the fragments is diatomic carbon, which fluoresces when energized by sunlight. This fluorescence produces the characteristic green hue that can overshadow the visual presentation of a comet's coma when gas production becomes sufficiently robust. The transition seen in 3I Atlas indicates that perihelion stripped away insulating surface layers, allowing volatile-rich material to erupt into space. Dust did not vanish. Rather, it ceased to be the significant contributor to what observers were witnessing. Astrophotographers around the world focused their instruments on 3I Atlas, documenting the same green glow that emerged post-perihelion. Among these observers, Ray's astrophotography provided particularly compelling confirmations through the use of ground-based telescopes and meticulous processing techniques. These observations echoed the results from large professional facilities, proving that the color was indeed real, persistent, and spatially coherent with the comet's coma. These amateur observations transcended mere color detection. By stacking exposures, reducing noise, and analyzing background stars with care, observers were able to pinpoint the comet's intrinsic features. The green emission remained fixed to the object's structure and position, eliminating the possibility of atmospheric effects or processing artifacts. Ray's imagery also unveiled structural details within the coma, enriching the narrative. Distinct jets and fan-shaped outflows were visible, extending outward in specific directions rather than forming a uniform cloud. These features indicate localized active regions on the comet's nucleus, where sunlight heats particular areas more intensely. As the nucleus rotates, these jets sweep through space, creating patterns and gaps that reflect the object's spin and surface heterogeneity. The green glow seen after perihelion is just one of the many peculiarities associated with 3I Atlas. Long before it turned emerald, it had already exhibited a series of anomalies that distinguished it from every previously observed interstellar object. According to Avi Loeb, examining these features collectively, rather than in isolation, reveals a pattern difficult to discount as mere coincidence. While the color change is striking, it sits atop a broader list of statistical, dynamical, chemical, and geometric oddities that continue to spark debate about the true nature of this object. One of the early anomalies concerns its trajectory. 3I Atlas is moving in the opposite direction to the planets. However, its path is aligned with the ecliptic plane to within about 5 degrees. For a random interstellar object arriving from deep space, such alignment is highly improbable, with an estimated probability of just 0.2%. Interstellar objects should approach from arbitrary angles rather than uniformly skim the flat plane shaped by billions of years of planetary motion. Loeb argues that such precise alignment is statistically suspicious and challenging to reconcile with a purely random origin. The direction from which 3I Atlas descended adds another layer of intrigue. Its inbound trajectory is coincident within 9 degrees with the location of the famous WOW signal. Just 2 weeks ago, I noted that the arrival direction of 3 Atlas aligned closely with the WOW signal, detected in 1977, which was an enigmatic, powerful radio signal originating from beyond our planet. The unexplained 1977 radio burst long associated with the search for extraterrestrial intelligence. The likelihood of this alignment occurring by chance is roughly estimated at 0.6%. While Loeb emphasizes that coincidence does not equate to causation, he also points out that repeated low-probability alignments become more conspicuous when considered together. Morphologically, 3I Atlas behaves in a way that is distinct from typical comets. Before and after perihelion, it displayed a persistent sunward jet, sometimes referred to as an anti-tail. In ordinary comets, such features are frequently optical illusions created by viewing geometry. However, in this case, detailed analysis suggests that the jet is real and physically directed toward the sun. Maintaining a sunward jet contradicts conventional comet behavior, as solar heating typically drives material away from the sun, not towards it. Loeb posits the possibility that this might indicate a technological, rather than a natural mechanism. Timing plays a critical role in the observed anomalies as well. The arrival of 3I Atlas seems finely tuned, allowing it to pass within tens of millions of kilometers of Mars, Venus, and Jupiter, while simultaneously remaining undetectable from Earth at perihelion due to its proximity to the Sun in the sky. The combined likelihood of such timing occurring randomly is estimated to be just 0.005%. Such precise sequencing suggests intent rather than randomness, especially when considered alongside what follows. Perhaps the most striking orbital coincidence involves Jupiter. On March 16, 2026, 3I Atlas is predicted to pass Jupiter at a distance of approximately 53.6 million kilometers, nearly identical to Jupiter's Hill radius of about 53.5 million kilometers, the region where Jupiter's gravitational influence allows for stable satellite orbits. Loeb notes that this is an extraordinarily rare coincidence and speculates that such a trajectory would be ideal for deploying artificial satellites or probes into orbit around Jupiter, potentially near its Lagrange points where minimal energy is needed to maintain position. The physical properties of the object further complicate the picture. The nucleus of 3I Atlas appears to be several orders of magnitude more massive than either Oumuamua or 2I Borisov, yet it is moving faster than both of them. According to Loeb, there is insufficient rocky material in interstellar space to naturally deliver an object of this mass into the inner solar system once per decade. This raises the possibility that 3I Atlas was not randomly selected from the interstellar population but rather targeted to enter the inner solar system deliberately. Its chemical composition also raises questions. Spectroscopic observations reveal that its gas plume contains far more nickel than iron, a ratio not observed in any known cometary body. Even more striking is its nickel-to-cyanide ratio, which is significantly higher than what is found in natural cometary bodies, with an estimated likelihood below 1%. Loeb notes that the ratios resemble those of industrially produced nickel alloys rather than primordial solar system material, suggesting that the surface composition may not be entirely natural. The behavior of the jets adds another layer of anomaly. 3I Atlas displays jets both towards and away from the Sun simultaneously. Achieving this pattern through ordinary sublimation would necessitate an unreasonably large active surface area to absorb enough sunlight to account for the observed mass loss. Loeb argues that this energy imbalance raises the possibility that the jets are not driven by sublimating ice at all but rather by an alternative energy source, which could be technological in nature. Near perihelion, the object also exhibited non-gravitational acceleration, meaning its motion could not be solely attributed to gravity. While such acceleration is sometimes seen in comets due to asymmetrical outgassing, the magnitude and context of the acceleration in 3I Atlas again challenge conventional explanations. Loeb suggests that an engine or propulsion system cannot be dismissed based on the current data. Finally, the geometry of the jet stands out. They are tightly columnated and maintain stable orientations over distances exceeding 1 million kilometers in multiple directions relative to the Sun. Natural cometary jets tend to diffuse and lose coherence over such distances. The sustained directional stability of these jets, according to Loeb, could imply active navigation, attitude control, or even the release of smaller probes from a larger carrier object beyond the immediate spectacle. The implications are profound. 3I Atlas offers a unique glimpse into the interior of an interstellar object, demonstrating that such bodies can retain volatile-rich layers across vast spans of time and space. Its green glow serves not just as a visual curiosity, but as a diagnostic tool, providing astronomers with insights into composition, thermal history, and internal structure. Each molecule fluorescing in the coma carries information about conditions surrounding another star long before the Sun exerted its influence. For a brief moment, as it traversed the inner solar system, 3I Atlas permitted humanity to witness those forces at play, illuminating the darkness with a glow both beautiful and deeply informative.